Okay, I'm doing this PowerPoint last and then I'm going to put it in front of everything that you'll see behind it. And what this is a discussion then of effectively how to use the TI-83, and I'm only doing that because in the end it should probably be your most efficient way to solve the single 2D or 3D concurrent force problem. If you remember, up to now we've basically talked about that what you need to do is you need to make a vector, you need to make a matrix basically where you had the direction of one vector here, the direction of the other vector, and the opposite of the knowns there. This is a 2D problem, or for a 3D problem the same thing stacked up. 1, 2, 3, the directions of the unknowns, and then finally here the magnitude and etc. of the opposite of the knowns, and use the RREF function. Alright, so what follows is a series of videos showing how you go about doing that and discussing the matrix algebra, how you do it in Excel, and so you can jump through these. If you can follow this right here, you can probably skip the rest. Remember that in effect we really looked at, if we look at any given stacked matrix, it really turned out to be the cosine of phi times the cosine of theta, the cosine of phi times the sine of theta, and then just the sine of phi. In other words, this is the x component, the y component, and the z component. So here's how you go about doing that in your TI calculator. First thing, you got to still sketch on the side the problem and identify the members that you're looking at and the immediate node, the concurrent point, as well as the neighbor nodes. That's so that you can do these subtractions, remembering that a node is a vector. Even though it's a point is a vector. A point is a vector. Otherwise, you wouldn't be able to subtract 2 points to get a line and then normalize that line to get a direction. So, sketch the problem, identify the members and the immediate node, the concurrent point that you're talking about, and then the neighbor nodes. This idea of a link node, you're right in the middle of doing it with your bridges. So you should be aware of naming each and every one of your members should have a number, and each and every connection should have a node when you're looking at that sketch. Alright, the next one is to put one node into each of lists 1-4. And remember how we do that. We kind of do the squiggly. If the node is 10, 10, 10, we squiggly, we do the store, and I put it in L1. Other ways to do it, you can do it in lists. Getting used to doing it this way gets you trained for a lot better stuff, and it's actually more efficient. So you put one node into each of lists 1 through 4, and usually list 4 is going to be the concurrent force. In other words, the point of application of, if you've got a 3, 1, 2, 3 different kind of tensile vectors coming out, point 4 is going to be the common point. Now, since you want the direction away from load 4, the tension vector, typically update each list 3 with list, for instance, list 1 minus list 4 back into list 1. So you go with this statement. List 1 minus list 4, and you're just more or less copying right back on top. So now no longer are you storing the points in list 1, list 2, and list 3. You are storing the line vectors, but only for a second. So right now you've described each of the runs of the cable, if you would. The next thing you do is you're going to normalize each list. In other words, divide the list by its length to get a unit vector in each of them. So you'll get a lambda. So here's the statement. You take each list 1 divided by the square root, open parentheses, sum of list 1 squared, close parentheses, store it back into list 1. So now list 1 is no longer a line vector, it is a direction vector. It is the unit vector lambda in the direction of the vector. We're going to go now, I guess, down through here, see if we can keep going. So each list is now the direction of the tension vector. So you have list 1, list 2, In list 3, each of them is a unit vector describing the direction of the vector. The next thing you do is you've got list 1 stacked like this, list 2 stacked like this, more or less list 3 stacked like this. You go ahead and use the list a matrix function. It's part of the matrix scenario there, that set of functions that you've got there. You put in something like this, and all of a sudden those 3 lists become a matrix G. However, matrix G has to be transposed, and so after you make this list a matrix, you have a matrix G, and you do this with the matrix function. You select the G, you select the transpose from the matrix math, and you store it into F. In the meantime, you've made a vector C, which basically is that vector which is the opposite of the knowns, which is usually going to be something like this. In other words, the weight goes down, and so you're going to have a positive weight here. What you're going to do once you've got G transposed into F, you're going to augment F with C. What that does is it slaps C onto F and stick it back into G. Remember, G was transposed into F, and now you've gone and added this kind of set of force vector, or the opposite of the knowns. And now with that G matrix, you can hit the RREF function and get a solution. And now, since you knew the directions of your vectors, right, you also now know the magnitude. And remember that any vector can be expressed by its magnitude times lambda. And because your list 1, list 2, and list 3 originally, right, because those ones were finally describing a direction, you can go ahead and stick it into AutoCAD by using the at function to get a unit vector, and then using that direction, either scaling it or whatever you're going to do to sketch up your concurrent forces. And in the end, you should be able to add them in 3D tip to tail to check. That's how you do it. The videos that follow will take you all the way, including SketchUp, but you should be able to try to do this with a problem or two, clicking around, using a little help, going out to SAL if you need it, go out to calculator help if you need it, but that's the set of functions you need to get. In the end, that reverse row echelon format, the first row at the end will be the first cable, the second row will be the second cable, and the third row will be the third cable, which will correspond to lists 1, 2, and 3 directions. Give it a try. Thanks for listening.